All right, so the request for problem 13.56. So I copied the problem down from the book. All right, so we have I minus plus HClO3, HClO minus. OH minus is written over the arrow. That is very, very common when that is a catalyst. So over the arrow indicates that this is a catalyst, and that produces IO minus and Cl minus. So in this experiment, they were taking the concentrations of the reactants plus the concentration of your catalyst. All right, and so the generic rate equation is rate is equal to K, I to some power X, or any variable you pick, Cl minus to Y, OH minus to Z. I always pick X, Y, and Z. All right, and so in order to get the orders, when you have three unknowns in your rate law, X, Y, and Z, you have to do 4 experiments. All right, we only had 2 in the one in the lab. We had to do 3 experiments. You always have to do one more than the number of substances in your generic rate law. All right, so this one is set up a little bit different. Normally in the book, you look at 1 to 2. You do not look at 1 to 2 in this setup. All right, so it's going to take a while to visually look at the 3 different experiments. The one that should stick out is this one. All right, why they didn't put that as number 1, I don't know, just so you would have to look. All right, and so experiment 3, everything is 0.01 molar. And all of the other 3, 2 of them are 0.01 molar, and 1 is 0.02 molar. All right, and so I always put the higher concentrations in the numerator and the lower concentrations in the denominator. So for every one of these, my experiment 3 rate law is going to be the denominator. All right, so I want to find I minus first. It doesn't matter which one you find first. All right, but here is I minus. It's the first reactant. Raised to the X, I'm going to do that one first. All right, so I see that when I look at experiment 2 and 3, all right, so experiment 2, you had 0.02 molar. These were the same. These were the same. One thing changes. That's what you're looking for. Doesn't matter what ratio you put. You can put experiment 2 over 3, or you can put 3 over 2. I would rather deal with the number 2 than the number 1/2. So I'm going to put it experiment 2 over experiment 3. And so I took the rate law of 2 and divided by the rate law of 3. All right, so I just plugged in the numbers from rate law 2. 12.2 times 10 to the minus 2 was your rate. All right, and so K2, and then you had your 0.02 molar of your I minus here. All right, and so this here is the only difference. I wrote the other ones in, but I canceled them out because the ClO minus was the same at 0.01. OH minus was the same as 0.01. So they canceled out. We're not changing the temperature. We're only changing the concentrations like we did in lab 10. All right, and so the K values are constant. They cancel out. All right, and so you get, when you divide your rates, you get 12.2 times 10 to the minus 2 divided by 6.1 times 10 to the minus 2. That is 2. And then, of course, 0.02 to 0.01, that is also a factor of 2. So you get 2.0 is equal to 2 to the X. And so you are first order with respect to your I minus. All right, I'm going to do Y next. Y is the ClO minus. Doesn't matter what order, again, you go in. I'm going to look at my ClO minus. Again, I'm going to use experiment 3 for all of these because that's the one where they all stayed at 0.01 molar. Experiment 1. So when you look at experiment 1, you see that your I minus is not changing. Your ClO minus is changing. Your OH minus is not changing. So you're picking 2 experiments where only one thing changes. And so here I'm going to take experiment 1 because that's a higher concentration divided by experiment 3, the lower concentration. All right, and so when I do my rate 1, again, it is for rate 1, you can look, it's 12.2 times 10 to the minus 2. And now you have K1, and then your I minuses were the same at 0.01. Your OH minuses were the same at 0.01. It was the ClO minus that changed. In run 1, experiment 1, it was 0.02. In experiment 3, it was 0.01. All right, again, we're not changing the concentration. So for all of these that have the initial rate method, your K's are going to cancel, and then you're going to have only one thing that changes. So you only have one thing. In this case, it was a ClO minus. Everything else is going to stay the same concentration and cancel out. So again, you get the exact same answer. You have 2 is equal to 2 to the y. And so y is equal to 1. All right, so now we have to do z. And z is the one and is definitely the reason why this problem is difficult. All right, so now we see that from experiment 3 to experiment 4. Experiment 4 had a 0.02 molar for your OH minus. All right, so your I minus stayed the same, your ClO minus stayed the same at 0.01. All right, from 4 to 3, we went from 0.02 to 0.01. All right, so this one is very strange because here we increased our concentration, which normally increases the rate of reaction, but this is a catalyst. So catalyst can work in many different ways. So this catalyst, when we added more of it, we got a smaller rate. All right, so we added more of our catalyst, but the rate went down. It went from 6.1 down to 3.0. All right, so make sure, I know this is odd, you got to write down the numbers they give you. And so the rate in the numerator is 3.0 because our concentration, we always pick the higher one. I always pick the higher one to be in the numerator. All right. Normally that also corresponds to either the same rate or a larger rate. This one is very strange. This one, you added concentration of your catalyst, but the rate decreased. And so when you put in all your numbers for rate 4 in the numerator, that's when we had our 0.02 for our concentration. Every time rate 3 was exactly the same in the denominator, every time. All right, we picked different ones on top because in the last one here, we wanted the OH minus to change, but everything else stays the same, so it cancels. Rate constants are the same. We're doing it at the same temperature. All right, but this is very strange because the increase in concentration decreased our rate of reaction. So when you take the 3.0 divided by the 6.1, you get a fraction, 1/2. You can put it in decimal. All right, so mathematically, I see the answer as z is equal to -1. Now remember, if you don't see that as the answer, if you put it as a fraction, as 0.049 whatever, to solve it, you have to do the logs. Doesn't matter if you use the ln log or the log log. When you take the ln of both sides, remember your exponent comes out in front. So this is the ln of 1/2. This is z times the ln of 2. To get z by itself, you divide by both sides by the ln of 2. That's how you get your z of -1. And now you have your rate law. You have your x, your y, and your z. So rate is equal to k, concentration of I minus to the first, ClO minus to the first, x was 1, y was 1, and then OH minus is -1. So when we look at the overall reaction, which I wrote over to the right, it's first order with I minus, it's first order with ClO minus, it is minus first order with respect to OH minus, and then you add them up. And so this reaction is a first order overall reaction. And so you can pick any run that you want to solve for K. They will all give you the same answer. All right, since my base was run 3 and everything was very simple at 0.01, I don't have to use my calculator. I can do this in my head. Doesn't matter which one you use, and you can get to use your calculator. All right, so I used run 3. All right, so it was the bottom every single time when I did my comparison of rates. All right, and so you have your 6.1 times 10 to the -2. K is what we're solving for. 0.01 to the first, 0.01 to the first, 0.01 to the minus first. All right, and then when you divide both sides by the 0.01, you're going to get 6.1. And now it asks for the units. Always K has units. So you can work out the units, or you can see that this is a first order reaction, and the units will be 1 over seconds. But if we look at the units, the rate was given in molarity per second. This is molarity, this is molarity, this is molarity to the minus 1. And so molarity to the minus 1 cancels out a molarity here. And so what we end up doing is dividing by molarity. So when we divide by molarity, they will cancel. And so your units, as you know, for a first order reaction for K is 1 over seconds. All right, and so there will definitely be a problem like this one. You have to show your work, or at least tell me what you're doing. So if you look at these up here and you can say, oh, I see from 3 to 2, I doubled my I minus, I doubled my IO minus, and so it is first order with respect to I minus. Fine, but you need to tell me that's what you're looking at and not just say x is equal to 1 because the coefficient in front of the I minus is 1, which is the wrong reason. You have to tell me how you're getting the x value of 1. All right, so then if you go from 3 up to 1 here, we doubled our concentration of the ClO minus. Both of these are the same. And I also doubled that rate. And so that is first order with respect to ClO minus. And then the very strange one. I doubled my concentration of OH minus, and I took the rate and I cut it in half. All right, and so that is a minus 1 order. So in that case, that one is very strange, and so you might need to put it into this type of setup in order to solve and get a negative 1. But if you can do that, you have to write what you're doing. You just don't write the answer and assume that I think you did it right. You have to tell me what you're doing. When it says show all work, even if you have to show me your thoughts, if you're not writing it down, you have to write out your thoughts if you're not saying or not writing out the equation like this. All right, so there will definitely be one of those on the test. Another one I picked out to do was the next one, 13.58. All right, and then that one, you have your cyclopropane converted to propylene. It is first order. It is not going to say that on the test. What it's going to stay on the test is your K is 6.0 times 10 to the minus 4, 1 over seconds. All right. I'm not going to say it's first order and give you the units for first order. I'm going to give you one or the other. And since the time can be minutes, it could be hours, it could be years, I can't just say it's first order and you say, oh, the units are 1 over seconds. No, it could be it's 1 over time. It doesn't have to be seconds. And so I will give you the units for K, or I will give you the rate with the units of time in it. All right, so you know that the units for first order is 1 over time. Most of the time it's 1 over seconds, not every time. All right, but these units tell you for sure that this is first order. So I will not write first order and give you the units. I will just give you the units, and from that, you know it is first order. And that's at 500 degrees Celsius. Again, your rate constants and your rate will change if you change the temperature, as we did in experiment 11. All right, they give an initial concentration. So your initial concentration, all right, so the initial concentration at time 0, 0.0226 molar. All right, now we want to know the concentration after 525 seconds. So after 525 seconds, so when T is equal to 525 seconds, I want the concentration of A at that time. All right, so since we know it's first order, you're going to be given your equation sheet as on Moodle. And so it is the ln of your A at time T is equal to negative KT plus the ln of A initial. All right, and so there is your first order rate law equation. You're given everything, you just plug it in, push the buttons on your calculator correct, and you will have your concentration. So we're looking for our concentration at this time. The K is given, minus 6.0 times 10 to the minus 4, 1 over seconds. The time is given. It says after 525 seconds. Key here, that unit of time and that unit of time must be exactly the same to cancel out. So if they were giving you the time in hours, you convert it to seconds. If they give you the time in any other units, it has to be in seconds to cancel the 1 over seconds. And then the ln of the initial concentration given as 0.0226. And so then you just get your calculator, push the buttons, and get your answer. All right, so when you take the ln of 0.0226, that is a negative 3.79. All right. Then you have your all right, so on the left, you will have now the ln of A at time t. When you push the buttons, that is a negative 4.1048, negative 4.1048. To get rid of the ln, remember the second ln button. All right, and so when you take your E to the negative 4.1048, you get your answer. And that is 0.0165. All right, so you have to be able to use your calculator, plug in the numbers, push the buttons, and you know it's got to be a smaller number. And so what you could do is calculate the half-life. All right, so if you want to make sure you push the buttons right, so you calculate half-life. Doesn't ask for it, but it's first order, 0.693 over K. Very simple. All right, so you take your 0.693 divided by the K value, 6.0, times 10 to the minus 4. And you get your half-life of 1,155 seconds. All right, and so we went not a half-life. So at the half-life, 0.0226 would go to 0.0113. And so this would take 1,155 seconds. Well, we didn't go that long. We only went 525. And so all this gives us is the answer is somewhere between the 0.0226 and the 0.0113. And we have a number between those two. It doesn't say that the number is correct, but it confirms that it is most likely correct. All right. And half-life for first order is consistent. So it could say, what is the concentration after 3 half-lives? All right, so after the first half-life and then the second half-life, or it could say, how long would it take? So the next one is 1,155 seconds. And so we cut this in half, 0.0565, 0.00565. All right, so you just have your calculator, you keep cutting it in half. And now for first order, the half-life stay the same. So it could say how long to go down to 25%. So here's 100%, here's 50%, here's 25%. So the time it takes to go down to 25% of your initial concentration, you just add them up. So 2,310 seconds. You would add those up. All right, again, first order, your half-lives do not change. First order, you know it's first order because of the units for K. All right, there will definitely be a problem like that with half-life, with concentrations at different times. Could be different percentages. So make sure you can do that. And of course, if we're going to do first order, we're also going to do second order. So the next one I'm going to do is the next one on the homework, which is 1360. All right, and so again, it tells you that it's second order. I am not going to say that it's second order. I'm going to give you K, and K is 0.169. Now, this is a weird way to write it, liters per mole second. You have to know that a liter per mole second is exactly the same as writing it as 0.169, 1 over molarity times seconds. Because liters here was down here, moles per liter second, invert and multiply, and so it becomes liter per mole second. So you need to see that this and this are exactly the same thing. That is writing the exact same mathematical thing. All right, so it gives you the units for K, so you know that it is second order. And now you have your sheet, you have your second order rate law, your second order integrated rate law, you got your second order half-life, and it says, how long would it take for, all right, so you have your initial concentration given. So they say your initial concentration for this problem is 0.159, and it wants the concentration, all right, so the concentration to be reduced down to, decreases to 5.50 times 10 to the minus 3. And they want to know how long is that going to take. All right, so again, you're going to have your equations. There has to be just one thing missing, and this time it's how long, the time. The last one, it was given the time, and it wanted to know what is your concentration. So there can be one unknown. All right, so you have to know the equation to use, and that is the 1 over A at time t, the second order integrated rate law, minus 1 over the concentration of A initial is equal to KT. And so now you just plug in your numbers. So once you get the right equation, you just plug in the numbers. So at time t, it is 5.5 times 10 to the minus 3. The initial is 0.159. The K is given, it is 0.169, and the time is what we are looking for. All right, and so get your number on the left. All right, so when you do that, you get 175.529. All right, and then you divide both sides by 0.169, divided by 0.169, and then you have your time. All right, and so everything in this problem was given to 3 sig figs, which means you should give your answer to 3 sig figs, which is 1.04 times 10 to the third seconds. All right, you can then leave that in seconds, or you can convert it to minutes. If it doesn't say what units it has to be in, you can leave it right there. All right, but some people don't know how many 1,040 seconds is, so you can divide by 60 seconds in a minute. So when you divide that by 60, you see that we're looking at 17.3 minutes. So people all can understand 17.3 minutes. If you tell people to wait 17.3 minutes, they know how long to wait. If you tell them to wait for 1,040 seconds, they're like, what? So a lot of times I will put it in terms of time that you can understand. All right, and so here we could also calculate the half-life. It doesn't ask that in that question, but no reason why it cannot. So let's answer the what is the half-life question. So now we are second order half-life. And so your T, 1/2, is 1 over your initial concentration of A times K. So the initial concentration, all right, so T 1/2 for this second order. And so your initial concentration was given as 0.159. And your K value was given as 0.169. All right, so the units here, it's molarity, and then this is your 1 over molarity times seconds. And so the molarities are canceling. And so your units are 1 over seconds, which is invert multiply seconds. And that gives you 37.2 seconds. So your half-life is 37.2 seconds. And now this one you may not want to check is terms of half-lives because 1,000 from this is going to be quite a haul. So anyway, but I'm just going to go through this. Again, 1 half-life. Remember, we are second order. This is 37.2 seconds to go from 100% down to 50%. That's what half-life means. Now, we plug this back in, but this is not 0.159 anymore. It is 1/2. So the next time we're putting it in for the second half-life, remember your first order only has K, and K is a constant, it never changes. All right, now for the second half-life, it is 1/2 of the initial concentration, 0.159 and 0.169. All right, it's half of it because that's what half-life did. It converted the concentration. It was 0.159, and now it is 0.0795. If I divided that by 2 correctly. 71998.105. Yeah, okay. So we're putting that number in. Put that, or just 1/2. We know it's 1/2 every time. Now when you plug that in, it doubles it. So to go from 50 to 25%, it takes twice as long. So times 2, so a 4, another 4, and then a 7. So 74.4 seconds. So if this time you wanted to know how long would it take to go from 100% down to 25%, you would have to add those two up. And so to get to 25% of the initial, it would be 111 point, the decimal point there, 6 seconds. And so you'd have to double that a few times to get to the answer that we had before. So that would be quite a lot of work, but it can be done. So the next one is twice as much as the 74.4. So, but here this is how long it takes to go to 25% of the initial. All right, so you have to know that every time you're doing first order, it never changes. Every time you do second order, it doubles. Why does it double? Because the initial concentration every time goes down by 1/2. And when you're dividing by 1/2, that is the same as multiplying by 2. All right, so there'll definitely be first order and second order integrated rate laws to do with half-lives. All right, let's try. We'll do one of these that, this one is 13.90. All right, so this is a mechanism. You know that because it labels them as slow step and fast step, and it also has the word mechanism in the problem. All right, so NO2Cl. All right, so the first step, you're going to call that rate constant K1, NO2 plus Cl. That one is slow, and this is great. If the first step is slow, that means that this is an easy question. NO2Cl plus Cl yields NO2 and Cl2. And the step is fast. All right, so all these questions are not hard. When the first step is slow, then this is a very easy question. All right, and so the first thing you're going to have to do is give the overall reaction. It should be very simple. We subtract 1 Cl from both sides. And so you have 2 NO2Cl. Oh, this was K2 because it's step 2. So this is called step 1. This is called step 2 of your mechanism. All right, and so that gives you 2 NO2s and ACl2. Here's your reactants. Here are your products. All right, and then the thing that we didn't label because it canceled out was the Cl. All right, so the only hard part about this, but that's not hard, is to label your Cl. So you see that you formed it, you didn't add it, you formed it, you didn't add it, you formed it, and then you used it. That is a reaction intermediate. Catalyst, like we did in the lab, you have to physically add that. All right, this was not added. It was not something that was added for the reaction. That would be a catalyst. This was something we got and used up. So Cl is a reaction intermediate. All right, so it's going to say label reactants, products, reaction intermediates, catalysts. There are no catalysts in this problem. All right, and so it says give the rate law. Well, you get the rate law from the rate determining step. How do you know which one's the rate determining step? Well, it's the one that's labeled slow. So again, very simple. Which one's the rate determining step? The one that's labeled slow. One of them will be labeled slow. That is your rate determining step. Very simple points to get. And so here you write the rate law from, that's why it's called the rate determining step. You write the rate law from that reaction. So rate is equal to K, your concentration of NO2Cl. NO2Cl is a reactant, and that is your answer. Again, the hard ones are where it's the second step, where you have an intermediate in there, and then you have to do a substitution to get rid of it. All right, and so this one would be a very simple question. All right, and so it is first order with respect to NO2Cl, and that's the only thing that we have, and so it's also first order overall. All right, and so the units for K would be 1 over seconds, or you could put the dimensions, which is 1 over time. We almost always use seconds, but it could be 1 over minutes, 1 over hours, 1 over years, and so the normal units that we use, 1 over seconds. But if you happen to put that the units for K is 1 over decades or something, as long as it is a unit of time, that is not wrong. So the units can be any 1 over unit of time. On the review for the test, I did one where it was a second step and you had to use equilibrium. So make sure you go through that. There may be one of both. There may be only one. You need to know how to do both of those types of problems. All right, let's go back up to this. We can answer these questions. So other questions that are simple, but people don't do them enough to feel comfortable with them. All right, so this problem should be, everything here should be simple. I can pick one that can be a much harder one, like the one on the review questions for the test. All right, so these are elementary steps. So steps in a mechanism are elementary steps. That means we can use the coefficients as the exponents. All right, because the steps in this reaction mechanism were determined experimentally. All right, which says that the exponents on these steps are the rate laws. It's the order for your rate law. All right. So when a step has just one reactant, that is called a unimolecular reaction. So step 1 is unimolecular, which means one molecule. Step 2, we have one of the NO2Cls, and we also have one of the Cls. And so this is a bimolecular. So you're only going to be asked if it's unimolecular, bimolecular, termolecular when they are steps in a mechanism. Those are the ones that are the elementary reactions. Those were done experimentally. If you wanted to write the rate law for step 2, it is rate is equal to K2, the NO2Cl to the first, Cl to the first. All right, that is the rate law for step 2. That could never be the overall rate law because it contains a reaction intermediate. Good thing that wasn't the slow one. Then we would have to do this would then be an equilibrium, and then we would have to use our rule for equilibrium, like you can watch in the video for the review for the exam. All right, when the first step is slow, all right, so you're adding stuff in the first step. And so everything on the left is either a reactant or a catalyst, and it is fine for that to be in the overall rate law. It is when step 2 or step 3 is the slow step, then you're going to have usually a reaction intermediate that you have to do by a substitution. So get the unimolecular, bimolecular, termolecular questions correct. Those are very, very simple questions. People get them wrong because they don't even know what that means. So again, if you do your homework, you will see these things, and they should be very simple. Okay. Oh yeah, let's do this one. All right, this one is 1378. All right, so you're given the reaction 2NOCl is going to go to 2NO and Cl2. All right, so all these are gases. All right, and so it has a rate constant values for the reaction. So here we are doing like we did in lab. So here they've calculated the rate and at a given temperature. So they're calculating the rate constant. So K1 is equal to 9.3 times 10 to the minus 6. At T1, right, and so this is 1 over seconds, all right, and so we just do this mechanism. I think we just, yeah, so good. So we just did this mechanism. Here's the overall reaction to NO2Cl goes to 2NO2. Oh, it's different. Okay. Anyway, but similar. It could have been the same. But anyway, this one is also first order. So the units for K tell us this is a first order reaction. Is that important for this problem? No, but it is a first order reaction. At T1, all right, now here you got to be careful because it tells you it's 350 Kelvin. A lot of times it gives you the temperature in Celsius. When we did the lab, you read your thermometer in Celsius and you have to convert it to Kelvin. So this is not a great problem because you don't have to convert it. You must convert all temperatures into Kelvin or you will get the wrong answer. And then read it at a different temperature and got 6.9 times 10 to the minus 4. All right, and that was at a temperature of 400 Kelvin. All right, and so this one is a two-part question. Part A says calculate your energy of activation, and then part B says calculate K at 435. Calculate K at 435 Kelvin. All right, so we see, of course, every time you increase the temperature, you're going to increase the rate of reaction. So what we do know about the K value at 435, it's going to be larger than the K value at 400. All right, but to find that, we have to have the energy of activation. So we have enough data to get the energy of activation, and then we will plug it back in and get a K at a different temperature. Because the energy of activation is a constant. It is not going to change. For this reaction, energy of activation is the same regardless of the temperature. All right, so you have the ln of K2 over K1 is equal to your energy of activation over R, 1 over T1 minus 1 over T2. That will be on your equation sheet. All right, and so you have your ln K2, 6.9 times 10 to the minus 4, 1 over seconds. Doesn't matter what the units are because they're going to cancel. However, when we calculate K, you have to give it with units. How do you know what units? It's the same units that they give you in the problem. All of the K values. This reaction is first order no matter what the temperature is. All right, and so then divided by 9.3 times 10 to the minus 6. 1 over seconds. That's your energy of activation. Here's where you can make a really dumb mistake and use the wrong R value. There's 2 R values. If you use the wrong one, you're not getting any credit. So that tells me you're not paying any attention to the problem at all. You're just randomly plugging in numbers and hoping you get the right answer. You have to know that energy of activation is in joules per mole. You must use the R value. That is in joules per mole, 8.314 joules per mole Kelvin. All right, and that is 1 over T1. Again, if you're not using Kelvin and you're putting a 1 over a temperature, and you could easily get 0 degrees Celsius, a very common. That's what we had for one of ours. We at least tried to. The ice bath should have been very close to 0. You can't divide by 0. This could never be in Celsius. All right, and so it is 350 Kelvin for T1 minus 1 over 400 Kelvin. T2. All right, then you just grab your calculator and push the buttons. The most common error here is to not have parentheses. Depends on your calculator. My calculator immediately puts a parentheses as soon as I push the LN. Hopefully yours does too. If not, make sure you manually put in the parentheses. Make sure you're paying attention to the exponents. The top exponent is minus 4. The bottom exponent is minus 6. All right, so when you get the number on the left, when you do this, you get 4.306677. 4.306677. Again, I don't round any answers until the very end. All right, and so then I'm going to multiply both sides. So that's what I get when I do that. Now I have to get rid of my 8.314, so I have to multiply both sides by 8.314. So I multiply both sides by 8.314 to get rid of my 8.314. And then again, you have to, if you set this all up, and I can see that you have set up and you're unable to solve it, you will get a lot of partial credit. To get full credit, you have to also be able to push the buttons correctly. And then you have to divide both sides by the 1 over 350 minus 1 over 400. All right. Multiply by 8.314, and then I'm going to divide by, in parentheses, 1 divided by 250. Minus 1 divided by 400. And I get 1, 2, 3, 4, 5. 1.00 times 10 to the 5th. Joules per mole. That is my energy of activation. All right, to 3 sig figs. So I only need 2 sig figs. Well, they've only given the K. That's iffy, and I'm going to go. I will accept 2 sig figs. When you do the LN of numbers, it changes how you do the sig figs. 2 or 3 sig figs would be acceptable for this one. All right, and so now we need to find the K. So now we need to find K, I'm going to call it 3. When the T is 435. All right, so that was then the part B. What is the K value when your temperature is 435? We've already used 1 and 2, so I'm going to call this 3. Now your equation, you can change it, and I'm going to change it to K3 over K1. You could change it to K3 over K2. Wouldn't matter. I want the K3 in the numerator because that's what I'm solving for. You can call it K2 over K1 and then call this a different K2 if you want. I've already had K2 up above, so I'm going to call this one K3. Energy of activation over R. 1 over T1 minus 1 over T3. All right, so what has to happen is that number has to be the same. That has to be a 1. That has to be a 1. If this is a 2, this has to be a 2. If you pick 2 and 2, you get exactly the same answer. It will not change your answer at all. But if you pick a K1 and then a T2, and then you're going to have completely wrong stuff, that K has to correspond to that temperature, whichever K and temperature you pick. All right, we have to include the K3 and the T3 because that is the question. All right, so now we plug in everything except for K3. ln of K3 over the K1. So we look up above and see what we have for K1. All right, same thing, 9.3 times 10 to the minus 6. That is equal to my energy of activation that we just solved, 1.00 times 10 to the 5th joules per mole. And that's why you must have the 8.314 joules per mole Kelvin, because that's the only way that the units are going to cancel. All right, my T1 was 350 Kelvin, and now my T is 435. And what we do know about this, as this K has to be larger than the K2. If it is not, then you have done something mathematically incorrect. This time we get the answer on the right. So we take our energy of activation, I already have it in my calculator, and I divide by 8.314. And then I multiply that in parentheses by 1 over 350 minus 1 over 435. And now I have that the ln of K3 over 9.3 times 10 to the minus 6 is equal to, and then again, for clarity, you want to put these in parentheses after the ln, always parentheses, 6.73, and then 2, however, 2, I'll go with 4. All right, at the end, I'm going to give, well, I will accept 2 sig figs, but I'm going to give 3. All right, now to solve this, we have to get rid of the ln again. To get rid of the ln, you must know you push your e to the x button. On most calculators, it is the second ln. So if you look at the second ln, that should kick out an e, and then raise that to the 6.732. All right, and so we end up with K3, the e to the ln just gets rid of the ln. You get your K3, 9.3 times 10 to the minus 6 is equal to, when you take e to the 6.732, you get 839. Then multiply both sides by 9.3 times 10 to the minus 6. And you get your K3. And that is 7.80, or, well, they're giving all these to 2, so we'll be consistent. That is 7.8 times 10 to the minus 3. So if K1 and K2 are the 2 sig figs, then K3 to 2 sig figs. Now, if you just put that, you're not going to have the right answer. It has to have units, and the units for this K are exactly the same as all the other units for K, which is 1 over seconds. This was 1 over seconds. This is 1 over, every time you have a K, it's 1 over seconds. The temperature does not change the order of the equation. All right, so 7.8 times 10 to the minus 3. So let's go back up here to the original. 7.8 times 10 to the minus 3. So K3 was 7.8 times 10 to the minus 3 at a temperature 3 equal to 435. So what we said was the higher the temperature, the higher the K. All right, so this was an exponent of minus 6. Minus 4 is definitely higher than that. And then minus 3 is larger than minus 4. So that is a consistent trend, and that is your correct answer. The units for K, 1 over seconds. Units for K, 1 over seconds. Units for K, 1 over seconds. Units for temperature, Kelvin. Units for temperature, Kelvin. Units for temperature must be in Kelvin. All right, that's all the problems I was going to work today. If you have any questions, you can send me an email. I can work them out and I can send them to you. Test is tomorrow at lab time. If you need to have at least 2 hours, probably 2.5 hours, consistent time. So you can come at 8:15. You can come at 12:30, or you can come at 3:20. We're going to be up in the lab, and we're going to use the lab. We're going to use 3:23 for our test. If we all don't fit in there, because 18 will fit in there, then we will have some lab space to use as well. All right. 8:15, 12:30, 3:20. And it doesn't matter which one you come to, but you need to come to one.